Hello everyone, welcome to the final chapter, chapter 37. The first lecture is going to be quality control over the radiographic equipment. The second video will be quality control over digital monitoring. So I'd like to go ahead and start here. Quality assurance is the overarching umbrella that every radiology department has, and as you can see, it encompasses all aspects of patient care, image production, and image interpretation. So QA, or quality assurance, has a written radiation protection plan, and it's monitored and evaluated. It monitors the radiation exposure for personnel. It ensures that we all have accurate techniques. Those are usually pre-programmed in the control panel. It looks at satisfaction surveys from patients. This also encompasses the equipment calibration and monitoring, which is called quality control, and then the repeat analysis, and then continuing education. How I remember the difference between quality control and quality assurance is people, and quality control is equipment. And just remember, you can't control people. So quality control, which is what we're going to focus on for this lecture, is all about the equipment. So there are specific calibration and monitoring tests that are done, and these are usually performed by a radiation physicist, usually on an annual basis. There are acceptance testings for equipment, usually at the time of purchase, and then there's a baseline performance for each unit, diagnosis of correctable deviations in performance. So if something goes wrong, there's a diagnosis to fix it, documentation of those corrections, and all of these guidelines were developed by the American Association of Physicists in Medicine. This is the chart that's in your book, and I just sort of put it on here. We're going to go through each one of these individually, but as you can see, most of these tests are done annually, with a few that are done twice a year. And then the acceptable range is the deviation, so from the deviation from normal that's acceptable. So we'll go through each of these individually, but I just put it all on one chart in the PowerPoint. So exposure timer, so that's your timer. Ensures that the exposure time is accurate for each unit. The most common device used to measure this is an electronic ion chamber, and this must be checked after repairs or any part replacement. The passing acceptance range for the timer is plus or minus 5%. So that just means the timer has to be accurate within 5%. The exposure time needs to be consistent for two reasons. Any change in the time affects the overall mass, which thereby changes the patient dose. This also determines the length of time the electrons are bombarding the anode, and we're going to discuss this next semester in physics. MA linearity is really evaluating the mass, the overall mass. But as you all know, you can set the same mass, but use either a short exposure or a long exposure. But you should have the same readout, the exposure readout. So your exposure index for 100 mass using a long exposure time versus a short exposure time should be similar. So the acceptable range is 10%. Anything beyond that means that your mass MA stations are inaccurate. And this is, again, there's two ways to measure this. There's an ion chamber, which keeps the time constant and measures the microgray per mass. Or you can just simply take 10 exposures at the same mass, but change the MA and time for each exposure and see if you get the same readout. The MA is actually the least reliable technique variable when you compare it to KVP and time. Exposure reproducibility is exactly what it sounds like. It's making the same exposure over and over and over again. So obviously, if we set a technique, we want it to be the same every time. So a simple test for that is you make 10 exposures using the identical settings, and the exposure index and the mass readout should be the same. and that acceptable limit is plus or minus 5%. It's a little bit tighter than MA linearity, because if you're making the same exposure over and over again, it should be the same. And this ensures that you're protecting the patient from overexposure, and that your technique is accurate. Half value layer is something that a physicist again would measure, and this is the most important quality to check for the X-ray beam penetrability. So the way you test this is setting a KVP and then adding aluminum until you reduce the intensity to half its original value. This is also the way you measure filtration. And filtration is the function that is used to reduce unnecessary or low energy radiation to the patient. So there are two ways you can increase the beam penetration. You can either increase the KVP, which is what we usually do, or you can actually increase the amount of filtration, and that will remove all the low energy beam X-ray beams, and you'll just have high energy X-rays left. So half value testing is plotted sort of like I have on this chart. At 70 kVp, you would need to add 1.6 millimeters of aluminum to reduce the intensity to half its original value. At 90 kVp, you need more aluminum to reduce the intensity to half because the beam is more penetrating. And then the same thing at 110. Don't worry too much about half value layer. We're going to talk about all of this again in physics, and then you'll get it again in radiation protection. KVP calibration is basically the same as reproducibility, and it's basically using the same test as the half value layer, but you're covering all of the KVP ranges, so from 50 up to 120. So the KVP accuracy has to be within plus or minus 5%, and that's what we use, but for federal standards, the federal limit is plus or minus 10%. The collimator light and field size also has to be measured, so the actual field size must match the light size. So the standard deviation for this is plus or minus 2% at 100 cm, which is 40 inches. So if the field size is greater, then you're giving the patient unnecessary radiation, and if the field size happens to be smaller, then the anatomy could be clipped. So this is why this is extremely important. So the collimator light projected onto the IR must match the collimator size indicated. So when you're manipulating the collimator, those numbers must match what is projected on your detector. And this is just showing you how you can check that. You can really check this on your own by putting, opening up the collimator, and then putting a coin on either side of where the light is, and then when you make the exposure, your light should be inside all 4 of those coins. That's just a simple way to do this. This would be so much easier if we could do it in class, because I could show you how to do most of these tests. The verticality of the CR and the SI indicators. So verticality of CR is just making sure that the center point of your X-ray light is within 2 degrees of vertical. So the actual CR should fall within 1% of the SID. And this, again, just ensures that your CR is in the center of your detector or the IR. The SI indicator, you can either measure that with a tape measure, which we do in class, or on most equipment it has an SID readout, which is actually on the collimator box. So the SID is measured from the actual focal spot inside the tube at the anode, and the SID indicator must be within 2% of the actual SID. And then this is just a picture of how you would measure that. So you can see on the top, on this picture right here, where the white arrow is, this is not, the CR is actually not centered. This one is centered. And you can see what happens when this isn't centered. Now you have this blooming effect that's happening over here, because now your X-ray light field isn't accurate. Focal spot size and condition is something, there's two focal spot sizes, and we're going to talk about this next semester in physics, so I'm not going to spend a lot of time on this one. But you have a small focal spot, which is typically 0.6 millimeters, or a large focal spot, which is 1.2 millimeters. And then this measurement is taken, it must be taken immediately following installation. But look at how large the deviation is. It's plus or minus 50%. And that's because when the manufacturers measure the focal spot, they use a low MA, but we operate our X-ray tubes at a high MA. So there's what's called focal spot blooming, which is just a phenomenon that happens when you're setting a technique at a higher MA. And then this is just showing you if you were gonna what the test looks like. So this is somebody who's setting the focal spot test up in a CT scanner. And so there's a slit camera or a pinhole camera, but they're both doing the same thing. Automatic exposure control, or AEC, it's essential that this is working properly, and the repeatable accuracy. So if you're repeating the same exposure using the AEC over and over, is the acceptance is plus or minus 10%. There's a total of 7 different AEC configurations, just so that you know. And usually you can do this test by making 5 exposures on the same photocell, and you should have a very, very similar readout. Again, we're going to cover AEC again in physics because it's a timer. So we're going to talk a little bit about that. And so AEC should also be linear, which means within 20% between the different rooms. So if you go from room 1 to room 2 to room 3, the AEC should be pretty consistent. And then just a final note that the +1 normal and -1 density controls actually determine the length of the exposure. And then the next things I'm going to be talking about are just a little bit more about the fluoroscopy. This is radiographic protection features, and then we're going to slide right into fluoroscopy. Again, we're going to cover this next semester as well. So the protective tube housing has a leakage radiation which cannot exceed 1 milligray per hour at 1 meter. The control panel must have a KVP and MAS indicator that should be visible to the technologist and the fluoroscopist. And then the SID indicator must be provided. Again, it has to be accurate within 2% of the SID, but in fluoroscopy, it's 3%. And that has to do with the fact that in image intensified fluoroscopy, it's not a rectangle collimator, it's circular. In fluoroscopy, the source to skin distance for these mobile units shall not be less than 12 inches or 30 cm, and then the SSD, source to skin distance for stationary units, should not be less than 15 inches or 38 cm. Primary protective barrier, so an image intensifier assembly, is lead lined, and that must have 2 millimeters of lead. That's PB is lead equivalent. And then the X-ray tube and intensifier must be interlocked, and the tube must not be energized when it's in the parked position. Again, filtration is a little bit higher in fluoroscopy. It's 3 millimeters of aluminum equivalent, because you're usually operating that X-ray tube at 120 kVp. And then in radiology for diagnostic tubes, it's 2.5 millimeters of aluminum. And then in fluoroscopy, the collimators must be adjusted so that an unexposed border is visible on the image monitor. So that just ensures that you're not, you don't have the collimators open beyond the IR. The exposure control for fluoroscopy has to be a dead man type, and that's usually a foot pedal or a hand pedal that's pressure sensitive. The Bucky slot cover has to have a minimum of 0.25 millimeters of lead equivalent. The protective curtain also has to be 0.25 millimeters. And the protective curtain should be positioned between the patient and the operator. When you're looking at a cumulative timer, we have a 5-minute timer, and that's just going to record the time beam on or fluoroscopy time on when you're fluoroing. And then it has a 5-minute manual reset. And that is it.